Today we're going to take notes on two variable inequalities. Go ahead and fold this into a trifold so we can start to explore how two variable inequalities are different than one variable inequalities. So I'm going to start by first flipping over to this side, and we are going to plot the points that are on this left side. Okay, so we're going to start by plotting points. The first point, 2, 5. -3, 1, -1. 0, 7. 4, 0. 6, -2. 0, 0. 1, 7. 9, 4. 2, -5. -6, 0. -4, -9. 0, -3. 4, 4. -4, +8. -3, -3. Okay, so we've got those points plotted. Real quick, I just want to talk about how two variable inequalities will be a little bit different than one variable inequalities. So if we look at a one variable inequality like we had on the warm-up, x is less than 1/8. When we try to graph that, there's only one variable to graph. So we'd only have a one variable number line, but there's just one number, and you would find the point where the boundary starts. So at 1/8 is where the boundary of this inequality starts. Am I going to put an open circle or a closed circle on 1/8? An open circle, because x cannot equal 1/8. And then when I shade the inequality, or I draw a line to represent all the values of x that satisfy that inequality, it's going to be to the left, because to the left are all the values that are smaller than 1/8 where we started. So that's a one variable inequality. Today we're going to look at two variable inequalities, how a y variable and an x variable compare to each other, and how then you can graph that. So, if there's everybody's graphed this on the grid, we can go ahead and flip over to the back side. So flip over to the back side, and hopefully we have this in a trifold. And we're going to look at the first fold. Y is less than x. So, what we're going to do is we're going to look at the places where y is less than x. All of the points on the grid where y is less than x. So, take a look at our points again. And somebody raise your hand and tell me, what is a point where the y value is less than the x value? I see Lila. -3, -1 is the y value less than the x value here? Or is -3 smaller than -1? Prisha? 6, -2. -2 is less than 6. 6, -2. Mohammed? Mohammed? Or Sam? 2, negative 5. Negative 5 is less than 2. Prisha? 9 and 4. Got any other people who want to name some points? Kaiser? Negative 4, negative 9 is another point. Okay. All right. Last 2 points, Matthew. 0, negative 3. What's your question? Put the dots. Kaiser? 4, 0. Okay. All right. So, those are our points. We put them on, and then we circled the ones where y is less than x. What do you notice about all of these points? Any pattern you notice? Sam? Sorry. There's a positive correlation. Isabel? They're all on the right side of the line, and that's not wrong, but I'd prefer if you could think about it in a different way. Is there another way you could describe something very similar? What'd you say? I thought I heard somebody say it. Kaiser? They're all below the line. So they are technically all on the right side of the line, but that aspect of it is not going to be consistent as we look at other types of boundary lines. What is going to be consistent is they're either going to be above or below the line. So that's what I'm looking for here. All of the points. Okay. Could we get a couple new points where the y value is less than the x value? Any point you can think of where the y value is less than the x value? Sam? 8, comma, negative 3. I'm going to go ahead and write that, and I'm going to plot it. 8, negative 3 is a point where that is true. Any other points? Lie below the line. Kaiser? 2 and negative 2. One more. 2, negative 2. Bunch.
5, negative 3.
5 and negative 3. All valid examples where the y value is less than the x value. So, when you do a two-variable inequality, when you go to graph a two-variable inequality, and I'm going to open up the illegal Desmos to illustrate this. Okay. I know. Okay. Y is less than x. You'll notice that the solution set is all of the places that are below the boundary line. So if the y value is less than x, all of my solutions are the places that satisfy this inequality. Or in other words, the places on the graph where the y value is less than the x value. Essentially what you have here is you're comparing the y value that you plug in to the x value that you plug in. And right now, it just happens that the slope of this line is 1 and the y-intercept of this line is 0. But you can have multiple different arrangements of this where the y-intercept changes or the slope changes. And in all of these situations, now this is a negative slope, my solution set is below the line because the y value is less than the line. Okay, so the right side is the representation of the line in slope-intercept form. and then the left side is the y value. And my solution is below this line. So what we're writing here is that the conclusion you can draw about shading an inequality where y is less than x is that you're going to shade below the boundary line, is what we call the line that separates my solutions from my non-solutions. And if I were to draw this, I'm going to use, just like they used in Desmos, I'm going to use a dashed line. So why am I using a dashed line? Let's take a look. Are these points 1, 1, 2, 2? Are these points where this inequality is going to be true? Is 2 less than 2? No. This is not a valid solution. So that dashed line represents the places where it is not true. And the reason why it's dashed, it's sort of like an open circle. When you have just a less than symbol, an open circle represents where it is not a solution, but it's the boundary of our solutions. When you have a less than symbol, the dashed line represents the places where the inequality is not true, but it again is the boundary of the solution set. So if I were to instead have y is less than or equal to x, in that case, I would have a solid line instead of a dashed line, because the solid line represents the places where it is now a solution, as opposed to the dashed line representing where it is not a solution. So back to our notes, I use a dashed line because this is not part of my solution. It's just the boundary from where my solutions go to being solutions to being not solutions. So y equals x is the boundary line. And I'm going to shade below, because everywhere below that line is a solution for this inequality. Yeah, go ahead. Okay, any questions about this first one? It's shading below the line because y's decrease as you get lower. So if you're at a given x and you just go down and down and down, all of these are going to be smaller than that x. Oh, it's okay. I was checking to see if that was confusion or... Yeah. How? Oh, just so that people who are absent can see? Yep. All right, sounds like we're ready to move on. So, the next one. Our equation is y is equal to x. So this time, we're going to circle all the points where the y value is the same as the x value. I see 4, 4. I also saw 0, 0 and -3, -3. All of these points are where y is equal to x. So y equals x is in blue. Y is less than x is in red. What do you notice about these 3 points? Okay. They're on the line. They are all on the line. So we could write a bunch more points that would fit this pattern. The only thing is that the x and the y value have to be the same. 1, 1, 2, 2, 3, 3. All are points. And this time, if we were to graph that, what conclusion would you draw about shading this? If all my points are on the line, where would I shade? Nowhere. You wouldn't shade. It's just going to be a solid line because it's equal to, y is equal to the x value, or equal to the line, equal to the boundary line, but you do not shade. You do not shade. Any questions about y equals x? That's very familiar. We've done that before. It's just a normal line. Okay. I assume there are no questions.
Wait.
Yeah?
I'm just writing.
Okay, no problem. All right. Let's go ahead now at the last section. We're going to look for the values of x where y is greater than x, or the points, the ordered pairs, where y is greater than x. So I see 2, 5, because 5 is greater than 2. I see 1, 7. I see 0, 7. -4 and 8, yep. And then -6 and 0. Oh, and I definitely always forget that one. -3 and -1. So all of those are points, and maybe we get the picture at this point, but what do you notice about these points? They are all above the boundary line. I'm going to pick just the easiest 3 points to add. 0, 1, 0, 2, 0, 3. My y values increase as I go up, so everything higher than 0 is going to be a valid point, or 0, 0. Everything above 0, 0 is going to be a valid point. And then again, what conclusion can we draw about shading? Shade above the boundary line.
They're all above the boundary line?
Yep, they are all above the boundary line. Okay, so I'm drawing the line y equals x as my boundary line. When I draw it, because my inequality is y is greater than x, would I do a dashed line or a solid line? Dashed line. If it were y is greater than or equal to x, then I would do a solid line. So the dashed line kind of is like an open circle. If it's not equal to, if y is not equal to x, then my solutions won't be on the line. They're only above the line because y is greater than x, but not equal to it. So
Wait, so if there were like solutions that were on the line, it would be straight?
it would be solid. Like as in like all of these dashes would be connected, just like that. A solid line, a dashed line.
Oh, okay.
Okay, great question. So I shaded above, and then my boundary line dashed because not equal to. It is not equal to x. Y is not equal to x, so it is dashed. Any questions before we move on to some practice examples?